Okay, so today we're going to talk about probability mass functions, or basically sampling distributions. Okay, and anybody listening at home or watching on YouTube, I can't do anything but that horrible noise. It's a horrible noise. It's coming from inside the room. The call's coming from inside the house. So there's nothing I can do. I have to apologize. So you can get the probability, plot the probability of any given score for some variable. So variable is just something, just have different possible scores, and then you've got the probability of getting that score, and you can plot that, graph that out. It's pretty simple. The probability of all possible events of all the scores added together is 1. Right? Think about a very simple example. Think about flipping a coin. You get a head or a tail. The probability of the head is 0.5. The probability of the tail is 0.5. 0.5 plus 0.5 is 1. The probability of all possible events is 1. If you add them all together, all the events. Okay? So that means that the area under the curve is 1. So if you were to figure out the area underneath a curve of these probabilities, and you plot the curve, and you've got that mass of stuff, that's what's called a probability mass function, or it's a density function, it would be 1 if you had all the possible scores and their probabilities. Okay? Does that make sense so far? Because if you get that, everything should be fine. If you don't get that, you're going to have trouble for the rest of the class.
Can you say that one more time?
You're going to have trouble for the rest of the class. No. I did it with the same intonation. You really did that? Okay, so there's a curve, and underneath that curve, well, the curve itself is all the scores along here, along the x-axis, and y has all the probabilities of getting those scores. Now, because the probability of all possible events, if you add them all up, is 1, right? Then the area underneath that curve, the amount of stuff in the curve, is 1. Does it make sense?
Yes.
Good. Okay, so the probability of all possible events then is 1. And the area under the curve then of one of these probability mass functions is going to be 1. It is always going to be 1. Unless you haven't plotted all the possible probabilities and you miss some scores. So as long as you plotted all the scores and all the probabilities, the area under that curve is going to be 1. So let's say we have a die roll, which is the sort of classic stats prof example. It's rolling a die, or it's flipping a coin, or it's drawing M&Ms out of a bag. Those are the ones we all use. In fact, M&Ms, the company that makes them, found out years ago that statistics professors were using the probability of getting a red one, a green one, a brown one, and if you write away M&Ms, you can actually find out the population distribution. They will do that for you. So if you send them an email, they will respond. They used to just publish these things and just send out the stats questions. It's pretty great. So this is rolling a die. The probability of getting any given roll is 1 out of 6. Right? So it's 1 out of 6. So each of those bars holds a 1/6. And 6/6 is 1. Right? 6 is 1. 6 times 1 over 6 is 1. Cancel the 6's, you get a 1. Very simple example. That's what's called a uniform distribution, equal probability for every single possible score. Okay. You likely don't think of things like this in terms of graphs. You think of them as the chance of getting getting any given die roll is always the same. This assumes a fair die, of course. You don't have to load the die. Okay. All right. So that's pretty straightforward. Now, that's just a way for me to introduce the idea of talking about a distribution that we care about more than any other, and that is the normal distribution. I typed normal distribution into Google image search, and this is the first one that came up. So the normal distribution is just like the distribution of virals. These are all possible x values along here. This is, in fact, a standard normal distribution because it has a mean of 0. It has a standard deviation of 1, so it's a standard normal distribution or a Z distribution, right? Right, it's a Z distribution. It's fun going to conferences. You can always tell people if they're American or Canadian. The easiest way is when they say, well, I did a Z test. And people, oh, you're one of us. Even if they're at an American university. That's hard when you're taught as a kid. So, plus or minus 1 standard deviation is 1, plus or minus 2, whatever. That's not really that important. The point is that the area under that curve, if we had these probabilities here, if I actually had the numbers here, just don't, doesn't matter, is we add all that up underneath that curve, it's 1. Think about it, when you look something up in a Z table, you get these numbers. You never get a number greater than 1 for probabilities of, say, up to and including that value. Move that over. So the most common, and I guess, distribution, and at least it's the most useful. It may not be the most common one. It is common enough in nature that we can make some statements like, I guess I kind of can say that, but there's a lot of examples in like intro stats books that are just wrong. The premise of them is silly, right? So when you first start doing Z tests in intro stats class, you get the probability of a light bulb lasting whatever is in days is, you know, has a mean of x and a standard deviation of whatever sigma, so mu and sigma, and then and it's normally distributed, and it bloody well better not be normally distributed. Right? Any light bulb company would want to skew all the hell over to the left, right? They want a great big hump on one side. They don't want to have a whole bunch of light bulbs that are, they don't want to have light bulbs that burn out as soon as you put them in, as often as ones that last really, really long. They go out of the light bulb business pretty quickly. So it's actually a bad example, but it's used a lot. Anyway, to us it's useful because we know some math behind this. It's got some characteristics. It is unimodal. It is symmetrical. And it's, quote, bell-shaped. Okay, so it's unimodal, symmetrical, and bell-shaped. So we can talk about its characteristics of shape. That's our distribution. And this is, we care about this distribution because we can use it in statistics, and we use it a lot, and it has some there's some really cool things that happen when you play with when you do some sampling. We end up with normal distributions while the population distribution we're interested in may not be normal, like the light bulbs. The sampling distributions are, which we're talking about today and next time. Okay, questions again. So far, good? Okay. I'm going to close the door. It's somehow going to make that sound worse, but it's not as bad as hearing people talk. So why is this useful? A lot of variables are distributed this way in the population. It is true. Probably things like human height are distributed normally. I think it's a pretty good guess. Right? I think, well, we know that IQ is normally distributed because the tests are designed that way. A lot of characteristics of biological systems go this way. So complex characteristics, things like height, that have that are multi-causal. Things like weight probably distributed. There are just as many people who are 7'4" as there are people who are 4 feet tall. You know, by the way, if you're American and you're male and you're over 7 feet tall, there's a 1 in 6 chance you play in the NBA. So if you're over 7 feet tall and you're American, there's a 1 in 6 chance that you play professional basketball. That's how few people actually are that tall. If every team, let's pretend every team has 2 7-footers, and that's probably not true, but that's easy enough. So that means just what? There's 32 teams or 31 teams in there? Or is it 30? Let's say it's 30. So there's 60 guys. Multiply that times 6. That means there's only 360 people in the entire United States. It's a really big country population-wise. That are that tall. That's a weird statistic I learned on the 538 website, which is a website devoted to statistics and politics. Sports. It's just basically something I like. So we can use these standard techniques. If a lot of things are distributed this way in the population, we can come up with some standard techniques, and of course, as you know, people have, to deal with this. In fact, one of the cool things is with sampling distributions, there's a thing called the central limit theorem. And sampling distributions of a population are normal. This is what this means, okay? So normal with a mean of mu and a variance of sigma over the square root of n. So what this is saying is, notice how it didn't say that the population has to be normal. It doesn't say that. It says no matter what, the population is your measurement. As long as it has more than one value, the sampling distribution will be normal. So if I said, and this is counterintuitive. I will grant you this is counterintuitive. If I flip a coin 10 times, how many heads should I get on average? 10 times. Please just share it. 5. Yeah. Of course, right? That was not a tricky question. It's a fair coin. You should get 5 heads. And let's do this an infinite number of times. It's a thought experiment. We're going to do that we're going to flip a coin 10 times an infinite number of times. On average, the most common thing we're going to get is going to be 5. We're going to get 6 sometimes, right? It's going to happen. And we're also going to get 4 sometimes, right? We should get 4 heads as often as we get 6 heads. Does that just make intuitive sense that we're going to be math right now? That makes sense, right? It just should happen. It's true, in fact. So, and it's going to be a little lower than 5, but it's going to happen. And then there's going to be 7 heads and 3 heads. And it's going to be a little lower. And then 8, 2, it's going to be a little lower. And then 1 and 9. And then sometimes we'll get 0 heads, and sometimes we'll get 10 heads. It's going to happen, but it's going to be not very common. Holy crap! We have something that has only 2 possible values, but the sampling distribution is normal. Dude! Now there is a mathematical proof of that, but I'm not going to share it with you because, well, there's 2 reasons. First, it's beyond the scope of this course. Second, I can't remember it. So, when I was in graduate school, they said, our prof said, there's the proof of the central limit theorem. You didn't need to know that. No, so, this is cool, right? So, what this is saying, first of all, is it's normal. It's going to have a mean of mu sub x, which is what we have here, 5. And it's going to have a variance of sigma squared over n, or a standard deviation of sigma over n. I'm not going to go through right now working out the sigmas. It's actually 10 times 0.5 times 0.5 square root of that. Doesn't matter. Just a binomial extension. The important point here is it's going to get The sigma is fixed, it's a parameter, but n changes, yes? We could change n, we could make it 1,000 flips instead of 10 flips, we could change it the other way. As sigma gets smaller, or sorry, larger, what happens to sigma over square root of n? N. Yeah, it gets smaller. So as remember that from school? So the limit of sigma over the square root of n as n approaches infinity equals 0. If n is impossibly large, anything over an impossibly large number approaches 0. What that's telling us is the distribution is going to get tighter and tighter and tighter as the number of observations increases. Right? Does that make, if the limit thing helped you, that's great. If you went, oh, grade 12 math, that's fine. If it doesn't help you, just think of this. As the n gets bigger, as it gets impossibly large, the variance will get smaller and smaller, meaning the distribution will get tighter and tighter. Does that make sense? Right? Does it not make sense? No. Okay. No.
I didn't learn that, so
well, that's too bad. But, so, the hell with you. But, I kid, because I know. Think about this. Let's think of a different example instead of something bizarre like flipping coins. Let's think about all Algoma University students as a population. Okay? They're all registered right now. All the people are registered in a single class right now. And we are going to measure their heights. And we can pretend we know what the mean is. Say it's 177 meters. Fine. If we sample 10 people, we're going to randomly choose 10 people each time. On average, we will get an average of those averages, which is a weird way to think. We will get a number that is the same as the population mean. We're sampling 10 people. There's what? Let's say there's 1,200 students. Something like that. More now. Let's use 1,200. But it's going to be pretty spread out because sometimes we're just going to randomly select people and we're going to end up for some reason with a whole bunch of short people. Sometimes we're going to randomly select people and we're going to get the men's basketball team. It's going to happen. Right? And they're taller. The chance of those two things happening is probably about the same, really unlikely. More likely we're going to get an average of around 170. Let's pretend we know that's the actual mean. So instead of sampling 10 people, let's say we sampled 20. The spread outedness of that distribution is going to tighten because we're getting closer and closer to measuring reality. This is one of the few cases where we can actually know a population number. We could literally actually go and measure everyone's height. It would be a strange experiment. I don't know why. It wouldn't be anything ethical with problems. It would just be a weird thing to get put into the ethics panel. I want to measure everyone's height. Why? Because it's a secret. That would not get past the ethics board. Believe me. We're not telling. We don't like that. I'm on the REP. We don't like, we're not telling. We reject this. Okay. Now what if I measured, so as n approaches infinity? Well, infinity in this case is not infinity, it's 1,200. When we measure 1,200 people, all the students go to school here, their heights, we're going to get an average of 170. Then we're going to do it again. We're going to get 170. We're going to do it again. We're going to get 170 because we're measuring the same thing every single time. What's the variance of a whole bunch of numbers that are exactly the same? Nothing. The variance of 170, 170, 170, 170, 170, well, it's 0. Right? Does that make sense? The fun thing about this course is I can actually see light bulbs going off over your heads. It's fun. So that's kind of a cool property. And the fact that we always end up with a normal distribution, even with something weird like flipping a coin that's binary, tells us there's something special with the normal distribution. So we'll have to keep that in mind. File that away for a second. Okay, shifting gears a little. Let's think of, here's a weird looking distribution you will never see in the world. This is what I like to call a triangle distribution. I don't think it exists, so I made it up. We'll call it a Brodbeckian distribution because no one's named it. So, let's say we want to know the probability of getting a score on this variable between 3 and 7. Sure, that's doable. There's an easy way to do this. You would do this with geometry. Right? Wouldn't be that hard, actually. You would just, the area under that curve is just geometry. We get a square. Yes, maybe it's a rectangle. But how do you get the area of a rectangle? Well, one side times the other. That's pretty easy. And then you got a triangle, half base times height. Yes, all that stuff you learned in grade 5 does come back at some point in your life. It comes back when you have to buy flooring. And you work out how much hardwood floor you have to buy, and then you go, oh my god, I have to know the shape. How do I? Oh, that's easy. And then you realize the room you have downstairs, the people who had your house before and renovated downstairs, they don't know how to use square. So it's more like a trapezoid. I don't need a square. I can also smell level. Things I've gone through in my house in the last 15 years. Wait, this room is 22 feet long. That's fine, except that here it's 11 feet wide, and here it's 11 feet wide and 3 inches. That's not supposed to be. I don't have a table saw. I'm going to go to the neighbor. You rip this, but at the end of this board, it has to be this one. My wife has a table saw because she's an artist. I have lots of pots and pans. We've completely flipped gender roles in our family. But if it's not a common shape, like, you can look at that and go, look at a triangle, look at a square. If it's not a common shape, you actually have to know how to do calculus. And don't worry, you don't have to actually know calculus to do this work, because some poor bastard did the calculus for you a long time ago. But this is done with calculus. So again, out of curiosity, I asked this the other day, how many people here have actually taken some calculus? Oh, it's a good chunk of you, that's nice. High school or university?
Yes.
Both? Very good, me too. Yeah. At Western, to do undergrad, second degree, and do a first year math course. So most people took applied linear algebra because it was made for people who were math majors. I took calculus for math majors because I'm an idiot. Near the end of the course, I was like, I don't know what's going on. And that's when I got up and left. I literally got up and left. And I told Cindy the story from the great prof, Dr. Kochner. He wrote a textbook. He was amazing. And he was this Orthodox Jewish man. And he had a prayer shawl. And he was very serious. And he had a really cool sense of humor. And he knew all our names. There were 7 people in the class. Which is really something, because we're a first year calculus class, we were all our names. And one day I was trying to learn about Taylor and Maclaurin series, and I couldn't get it. I was lost. And I just got up. This is in March, and I was doing really well in the course. And I stood up. Mr. Brodbeck, where are you going? So I'm going, this is no fault of yours, sir. I've tried, I don't understand this, and I'm working really hard, but I don't get it, and I'm going to tutorials. I'm sorry, I think I'm wasting your time, and you are wasting mine. But it's not your fault, this is all on me. He said, so, well, where do you want to go? I said, I'm going to go to Spoke and have a beer. One of the bars it was. He goes, well, good luck, Mr. Brodbeck. He was awesome. He's the guy I once told in that class, in that intro calculus class, he said to us, at one point in your life, if you don't know the answer, just guess 7. It's bound to be right at some point. Just sheer randomness. And I did use that once in graduate school. I just wrote 7. And it was right. It was great. So, in fact, you would take the integral. Oh, look at that! I don't know what that means. All this says This is that funny sign just means calculate the area under a curve, taking the integral, and of f at x, that's the function, and give it to me between 3 and 7. That's what that is. There's a way to do it. You'd have to know what the function looks like the equation of it. And actually, it's not hard to do. It's not a hard thing to learn how to do. It's very mechanical. And yeah, it's really not too bad. And then your calculus class, they say, now imagine if it was being spun around. You go, oh no, that was a solid. That's hard. So, you might say, I don't know calculus. Well, it's too bad. It's too bad that not enough people know calculus, because calculus is actually beautiful. It's the first time when you're taking math and you go, oh my god, the universe is really cool. Like, when you're doing math before that, you're going, oh, this is neat, okay, geometry's cool, okay, improving identities, that's kind of, trigonometry, that's interesting. And then this, you go, how does that even work? Why is that okay? It's neat. Calculus is really neat.
What is it?
What is calculus?
Yeah.
It's the study of area under a curve and changes in slope of distribution of equations. But it's math that describes the universe is the best way to describe it. It's a beautiful thing. Calculus is neat. It really is neat. And if you don't know any, I'm not saying go take a calculus class, but there's got to be videos on YouTube and stuff, just intro calculus videos. Just watch them. It's neat math. Okay, that's the normal distribution. That's actually the formula for the normal distribution. So f at x, that's the y, right, is 1 over the standard deviation times the square root of 2 pi times e to the negative x minus the mean divided by 2 times the variance. I'm never going to ask you this. We'll do that. If you do know calculus and remember taking integrals, that's a horrible integral to take. That would not be a fun one to do. It's ugly. You know what pi is? I'm sure you all know what that is. E is another mathematical constant. It's 2.7182818, blah, blah, blah. It's just another mathematical constant, okay? So you can just take the integral of this function, which is not easy. But what you would actually do, and then you take the integral and then put in, say, 95 and 107. Let's say you want to find out the IQs between the probability of having an IQ between 95 and 107. First of all, you take the integral, so you'd have, this would be 15, this would be 100, this would be 225, right? Because that's just the standard deviation, the variance, and the mean for an IQ distribution. And you go from there. And in fact, typically that's actually what you're doing when you look things up in a Z distribution. That's kind of what you're doing in a Z table. Now, you could make it a little easier. What if we made the mean 0 and the variance 1? In other words, the standard normal. This is a little bit easier. In fact, that's an integral that one could take a lot more easily if one had practiced doing integrals past 1985. Myself here. I've done derivatives since, but I haven't really taken it in ages. Calculus comes up a lot, sort of theoretical stuff in biology, so I've played with derivatives a bit, but not with integrals. So it is easier looking, right? Because we've taken the variance and the standard deviation made it 1, we've taken mu and made it 0. That's a little easier. Like you can see, it's a simpler equation. Still, it's not super easy. But what if we had a way to represent everything, instead of using that complicated one, make it a little simpler, and we could represent everything as where it falls in a distribution with a mean of 0 and a variance of 1. Well, that's what we do with the z-score. Right? So what I'm doing here, I've got 95 minus 100, Remember I'm saying I'm trying to find out the IQ, the probability of having an IQ between 95 and 107. So for 95, the Z value is negative 0.32, and for 107, the Z value is 0.466. That's the distance between the mean, which is 0, and that Z value. And I just looked that up in a table. Actually, truth be told, my calculator did it for me. My calculator has built-in Z distribution function. You can also do it, I'll show you in a second. There's a really nice web tool you can use that will actually build this for you. So all of this is doing is I've taken 95 and 107 and I've converted them into these Z scores. Okay, so I know that 95 is negative 0.32. It's probably that far. And 107 is 0.466. That's what 7 is there. I looked those up and I added those two things together, and I look up the probability of those two things in the score in the table, and I get 0.310. The probability of those Z values, I look them up on the table, and it just tells me. Okay? So look up those probabilities, and it tells me that the probability of getting those two, of a score in this range, is 0.31. This is something you did in intro stats, right? This is something you played with before. Questions? So I just looked it up in the back, in the table in the back of the book. Any stats book has a Z table in it. And draw yourself a picture. It's always good to draw yourself a picture, because then the top of the page almost always has a picture of what the entries are about, and then go from there. Fine. Look, no one does these things by hand typically. Something like this I might do by hand because it's quick. I'd probably use a computer. See, someone did the calculus for you. So instead of having to know the integral of the normal distribution and take the integral and then put the values in, somebody did this for you. A bunch of probably graduate students a long time ago did this by hand for you. And then they produced these tables. And they're just probabilities of getting certain Z scores. They're areas underneath a Z score. A Z distribution. It's area under the curve. Somebody did that for you. So now you just look it up in a Z table. So every time you look something up in a statistical table, I want you to quietly thank the people who are long dead who did the calculus for you, so you don't have to do the calculus. Right? So there's a web tool, there's a link there, and I'll show you after, I'll show you what it looks like in just a second. But there's a lot of, look online, look for Z distribution calculator, something like that. You will find all kinds of stuff, really good, easy to use. So you don't even have to look things up in a table anymore. So that's the link there, so take a look at that at some point, and you'll find, well, it looks like this. You put in the mean, you put in the standard deviation, and I put in these two. I said, I want between those two. And look, it actually draws me a picture. Well, it's a nicer picture than I do on the board. And then it gives me the answer. 0.3049. What did I say? 0.301? Okay, so. Because probably my tables didn't go to as many decimal places. By the way, you get exactly the same result if you put in 100, 15, and then 95 and 107. Exactly the same probability. The thing about the standard normal distribution is it made the calculus easier for everybody when they were originally doing this. This is why we go to zero when near zero standard deviation 1 was so people could take the integral easily. So they could actually find out the area under that curve easily. So all you do is turn everything into Z distribution, or standard normal Z distributions, or Z scores. That's all you have to do. Questions so far? Okay. Now in a second I'll show you the we call it that web tool, and also we'll do some SPSS stuff. But I'll show you some SPSS stuff. I said some poor person did the calculus for you. Just think back. Probably had no money. Some poor graduate student just sitting there toiling away, thinking, I can't believe part of my PhD thesis is just doing these calculations over. Not so much with the Z, but when we get to the T distribution and the S, we know that was graduate students who did it. Well, the F for sure. The T was weird. The T was a guy who was a statistician working at a brewery. It's like my dream job. We just look stuff up in tables now. Or you can use web tool, or there's all kinds of other possibilities that allow you to figure these things out nowadays. This isn't that scary. This is stuff you've done before. It is unlikely it was shown to you in this way, because frankly, when you're doing 2126, the intro stats, the idea is, can you just do this? Think about this. If when you were in second year and taking intro stats and you were shown stuff from this sort of theoretical angle, it would scare 90% of the class into dropping the course. There's a reason, and then, I know, you guys will be fine. You go, yeah, okay, cool. But you guys are the people that want to take another stats course for half to. Most people are like, I don't care. They aren't the guy like I was in my intro stats class that kept going, yeah, but why? It was like I was a 2-year-old. But why? And then you get the answer, the standard professor answer, I'm sorry, that's beyond the scope of this course. All right, so I'll stop recording here, and I'll show you that web tool.